Welcome back to this discussion on the respiratory system. In this second set of lectures, we are seeing the first now on gas exchange and transport. And this will cover topics up through the regulation of ventilation, and then we'll consider that regulatory system in the second lecture from this chapter 18 from the present version of the textbook. Well, this chapter then is going to talk about diffusion and solubility of the gases, the gas exchange in the lungs and the tissues, the gas transport in the blood, and that's what we're going to consider in this series, this portion of the series, and then the second set of this set will be the regulation of ventilation. As an overview then, we recall the oxygen and carbon dioxide move into and out of the blood at the pulmonary and the systemic capillaries. So we talked a bit about the pulmonary exchange in the previous set of lectures. Now we'll focus on that a little bit more. And in this idea of gas exchange, we think of the exchange on both sides of the circulatory systems or circuits, the pulmonary and the systemic. And so we'll go through these in a series of steps. The oxygen exchange at the alveolar capillary interface. Then we want to think about conditions for transport. So the exchange occurring at both places simultaneously. Remember, when a red blood cell leaves the left ventricle, a red blood cell is coming into the right atrium. And as well, we can think now when a red blood cell is passing through a capillary in the lung, a red blood cell is undergoing the gas exchange there. A red blood cell is passing from arteriolar to venous side in the systemic capillary beds also. So simultaneously, when we get the O2 taken out of the blood and the CO2 put in at the tissue, we want the same amount of exchange occurring at the alveolus, so that on a net basis for the whole organism, you have no net gain of O2 or CO2, or no net loss of either of those either. So we are at homeostasis. So the transport is in between. We can't ignore it. Otherwise, how are we going to get an effective and balanced homeostatic exchange at the level of the tissues, as we had talked about before, and then the carbon dioxide on the other side. So we will consider in this lecture these complex systems that operate on that global level. Like I said, what happens here is being balanced, is balancing against what is happening here at the tissue. You can get changes at the tissue once you start working out that will create a situation that will trigger a change up here so that there will be a slight transient imbalance, but that will be recaptured very quickly under normal conditions in somebody who's healthy. If you're out of shape and you start running, you can't compensate very well, and you're huffing and puffing and walking by the time you get to the corner. So remember, that's a big part of what we're thinking about here globally, and we're going to simplify it, but to look at first the oxygen system and then the CO2 system staged for the different locations, the pickup, the transport, the exchange at the tissues, and then we'll do the CO2 going back. So remember that they're happening simultaneously, and we have to reduce it and compartmentalize it to get our first feel for it, and then we begin to apply it and think about it. So it'll come back with the integration studies, as you know, when we start talking about responses to exercise globally. Well, obviously, diffusion and solubility are key biophysical properties that we need to think about. So there are constants. The surface area, we really don't change it much. The membrane thicknesses, if they change, then it's a pathology. And as well, the diffusion distance. So these are all interplaying with each other to generate the normal homeostatic condition. A few of these things can change when we exercise. So surface area is one thing that can change. We've talked about the ability to vascularize muscle tissue when you're getting into shape. So part of the conditioning is to vascularize. As well, the utilization of more and more alveoli can be, the efficiency of that can be enhanced by getting into shape as well. Just the mechanics of ventilation. Okay, so once you reach a steady state of being in physical condition, they are constants again, but they can be transient in between states. So I'd like to emphasize this every time we encounter these things, because traditionally they're presented this way and you think, oh, they're always the same. Well, they aren't. They can be dynamic and they will be transient. Some of them, the membrane thickness shouldn't change as you get into shape, but the capability of increasing the surface area of the lungs that is being used for gas exchange does increase with getting into shape, as does your ability to mechanically change the volume of the thoracic cage. But once you're in shape, then it becomes a steady constant again. So remember, there are constants that determine certain biophysical properties, and then those can be transient to go from state to state, from normal healthy to ultimate performance, and either of those into pathology. Concentration gradient is always something we recognize, and obviously is the most important factor. The movement of gases, so we've always, if you watch football, you know, sometimes they'll, the one thing that they can change, even though they've maximized and they're at a steady state for all these constants, they'll go to the bench and they'll suck up some oxygen, and so they're playing with this factor here that they can influence to improve their performance. So the movement of gases, the pressure gradient, the solubility, and the temperature are very important. So quite obviously you need to read more extensively on these topics in the textbook to get an enhanced feel for these, and the opportunities to do the quantitative problems in the textbook you should take advantage of also to gain a better working knowledge of these parameters for determining some of these biophysical properties and how they are assessed under normal conditions, or how they would appear under normal conditions and under abnormal conditions, or just transients within normal range from resting to active state. And the reverse, how do you recover resting state? So the pressure gradient, the solubility, and the temperature. So these are all taken into account in this series of slides that we'll look at, where we're considering a start point and an end point. So we're going to look at the dynamic changes. So we have the transient and we have the state, the initial state, the intermediate state, and the end state. These gray arrows show additional transients in between, so you have a continuum of this point of a PO2 of 0 to this point with a PO2 of 100 millimeters of mercury. So we start here. What happens when we add this gas? Say we started with a vacuum, and then when we had the water under this condition with no oxygen in it, completely degassed water, and we add the gas to the vacuum head. So we've got a gas head now that has a PO2 of 100 millimeters of mercury. So this is initial state, S sub I, right? And S sub M for middle, if you want. We know that the random movement of the oxygen molecules are going to have some probability or frequency of collision and interface with the surface of the water. Some of the oxygen molecules will penetrate and go into the water. They will become dissolved. And this is a natural phenomenon that is ongoing all the time at the interface of the gas-liquid junction, or the gas-liquid interface, right? This is a constant event that's going on all the time. You don't start with this. We're typically at this point here, and just some variation between these two, more or less in the gaseous state versus the dissolved state. So we're not going to see this. This is just for illustrative purposes to see how we can get from a PO2, when it's totally degassed water, When we deal with a PO2 in the gaseous state of 100 millimeters of mercury with an oxygen concentration of 5.2 millimoles per liter, what can we reach at end state when it is at equilibrium? Remember, equilibrium is a very common endpoint for all of these discussions. The PO2 is going to equilibrate at 100 millimeters of mercury, but the concentration of dissolved oxygen is not going to equilibrate. It's going to be a very small fraction of the total concentration in the gaseous state to produce the same PO2, partial pressure. So 0.15 millimoles per liter of oxygen will generate a PO2 in solution of 100 millimeters of mercury, whereas it requires a higher oxygen concentration in the gaseous state. So these are the games we're playing. So we see those same parameters for oxygen on the left, and now we compare to the carbon dioxide on the right. So this is what I said we would do. We look at oxygen in each case, and then the CO2. So the CO2 is different. A PCO2 of 100 millimeters of mercury in the gaseous state will still be 5.2 millimoles per liter. But to generate a PCO2 in solution of 100 millimeters of mercury, you need a much higher concentration of carbon dioxide, 3 millimoles per liter, than you do of the oxygen. So you can more easily produce a PO2 of 100 millimeters of mercury with dissolving oxygen, as long as the oxygen is as soluble, right? So if oxygen is less soluble, it'll be harder to get a little bit in there. So these are the factors that you need to think about relative to this. You're not going to change the rate at which they bump into the surface of the aqueous medium at a same concentration, right? Remember Avogadro's number, so are you going to have the same number of molecules? And if you are, which in this case we would, of course, then you'd have the equal likelihood that they're going to be colliding with the surface and having opportunity to dissolve. Then the only variable that differs is their ability to dissolve in the aqueous medium, so their solubility. So this is how we're playing this game with the variables that we saw on this prior slide, and I'm going back to it: pressure gradient, solubility, and temperature. So we saw solubility. If you have a high pressure gradient of the PO2 of 100 in the gas and a PO2 of 0 in the aqueous, obviously the movement is going to be from gaseous into the dissolved state. And then temperature is just going to increase the rate of movement of the molecules, right? And increase the solubility as well. So it's easy to see how those parameters come into play. We're not pushing a formula on you to do any type of calculation in this case, but quite obviously they exist, and such exercises would be expected in a professional education level. So we're still at undergraduate here, so we'll just leave it to the side and move on to this idea of the gas diffusion to start putting some numbers in our head. What is the PO2 and PCO2 in the alveoli and in the blood on the alveolar side of this game and the tissue side of this game? So the two sides where we said we have this balance. One event has to be balanced by the other, otherwise you have homeostatic imbalance. So oxygen on the left, CO2 on the right. As I said, we consider each separately, but they're going on simultaneously. You don't have two separate blood supplies, right? Now you take this and then superimpose it upon that, and you've got both going on at the same time. So we're reducing it to try to make it easier to understand. But what I will do is to do each jumping from left to right, since they're both on the same slide. So when we consider the pressure gradient, 100 millimeters of mercury PO2 in the alveoli, 40 millimeters of mercury for PO2 in the pulmonary arterial supply, right? So the pressure gradient obviously is favoring oxygen moving from the alveolus into the plasma. 46 for the PCO2 in the pulmonary arterial supply, and at the capillary bed, right? The arteriolar side of the capillary bed and the venule side of the capillary bed is what we're talking about. When it comes into the capillary bed, it's at 46. And that is 6 above the alveolar PCO2. So obviously we favor movement out of the blood into the alveolar gas. I don't want to call it air because it isn't air. It's going to become stale air, right? So on the venule side of that capillary bed, the PCO2 would be 40. So this is very important. So if we also make this a little more global, if we measured left ventricular PCO2, it would be 46. If we measure, right ventricular, hopefully you corrected me immediately, right ventricular PCO2 should be 46. Same as right atrial, right? That's all deoxygenated blood. Left atrial, left ventricular PCO2 should be 40. So across the pulmonary circuit, we should drop 6 millimeters of mercury of PCO2. With oxygen, we should jump 60 millimeters of mercury for PO2. At the tissue side, we're going to pick up 6 for PCO2, and we're going to drop 60 again of the PO2. So the PO2 is less than or equal to 40 millimeters of mercury within the peripheral tissue itself, so that the partial pressure differential from the 100 to the 40 across the capillary bed of the systemic capillary system doesn't automatically turn into a 60 millimeter mercury within the peripheral tissues. Okay, so it averages out through all the peripheral tissues to be less than or equal to 40 millimeters of mercury. That's the homeostatic level. So this exchange of 60 millimeters of mercury of PO2 at tissue and simultaneously picking it up at the alveolus, at the lung, is important for this homeostatic level that hovers around 40 millimeters of mercury in the tissue. Any imbalance that changes this exchange here or this exchange here independently or simultaneously is going to throw this off, and if it's not right, if it gets too low, you'll pass out and die, right? Or you have, if it's restricted to just one organ, like an obstruction of think of a thrombus or an embolism, then whatever's distal to the blockage is going to experience this drop below this normal level. You also don't want to build up more than 46 in the tissue. So notice that the venule side of the systemic capillary bed is at homeostasis with the tissue. So if you measure venous PCO2 and it is higher than 46, you expect that that's the same that you would find in the peripheral tissue. So this is an important relationship here. So the PO2 in the tissues is going to be roughly equivalent at any one point in time to that within the venous blood, and the same for the PCO2. But you got to be dumping in the equivalent of 60 millimeters of mercury to sustain the homeostasis in the peripheral tissue. So you can take a look at the animation for this on the CD if you have it. Now continuing on with the partial pressures, the normal blood values in pulmonary medicine. These are the values that you'd see in a clinical chart. PO2, PCO2, and pH. So these two interplay tremendously, and that's what we're proceeding to in our studies. The arterial side and the venous side, so PO2 is going to be about 95 millimeters of mercury on average, a range from 85 to 100. So there's always a target mean and a range on either side of it that will describe normal values. And this is, all people in the human population, essentially. The venous side, and then just about all animals, it's very close to this too. The venous side be 40 millimeters of mercury. And the PO2 is 40 and 46, as we saw. So the range is 35 to 45 for the arterial side. So the arterial side is really representing best the pulmonary function, and then it can be diluted out in the after the systemic circulation. So remember, arterial gases, blood gases, represent what just came from the lung. So you're not going to lose a lot in the left atrium, the left ventricle, and the aorta, and the artery from which you sample the blood. So this is a direct reflection of what just came from the lungs, the pulmonary function. So that's why this is pulmonary medicine. Venous is after the systemic exchange. So a lot of things can happen there to give you values that aren't reflecting exactly what is happening at the lung side. So obviously you can auscultate the pulmonary the lungs and have some other assessments to know if you should be suspecting any problem that would be a medical indication to make an arterial draw. These are higher risk than superficial venous blood draw, as you might very likely know. It's pretty tricky to get an arterial line, and it's higher pressure, so that's a higher risk. So you have to have a strong justification to do the arterial draw. So you can use these values just to get a good feel for how the full system is working. But if you think there might be a pulmonary compromise and it's not reflected by these, you'll typically see the doctor will order an arterial draw to do the arterial blood gases. But this can be done very quickly, and you can do other tests to get some assessments, and then, unless it's an emergency situation, you can delay doing the arterial stick a little bit and use that at a later stage to contribute to the differential diagnosis. So with the pH, we see the typically reported 7.4, but there's a range, 738 to 742. So anything outside of these, you begin to worry that something's going on that is outside normal homeostatic mechanisms. The venous side is roughly 737, and we don't get too concerned about variance there, but typically the venous side is where we make the measurements on the pH as well. So the same range basic range, it may be adjusted a little bit, but not much, to be triggers for concern. Well, this gas exchange, then, we talk about the classification of hypoxias. So a hypoxic hypoxia under type, then definition, and then typical causes. So it's a low arterial PO2. So a hypoxic hypoxia. So these can occur at high altitude or with alveolar hypoventilation by whatever cause. Holding your breath is one example, but something obstructing the airways so it doesn't get to the alveolus. Decreased lung diffusion capacity, or an abnormal ventilation to perfusion ratio. So it can be a blood flow thing too, remember that. Not just ventilation, as with the alveolar hypoventilation, but it can be a compromise of perfusion that can reduce the amount of O2 getting into the lungs. So notice they're saying arterial PO2, not venous. Anemic hypoxia is a decreased total amount of O2 bound to the hemoglobin. So blood loss, other forms of anemia, low hemoglobin or altered oxyhemoglobin binding. That's kind of a weird way to show it, but anyway, whatever might affect the ability of the hemoglobin to bind the oxygen. We'll look at those variables in a while. Carbon monoxide poisoning, which is one that actually impacts that because it occupies the hemoglobin that exists and it doesn't let go. So the affinity for carbon monoxide for hemoglobin is much higher than oxygen, and so it displaces the bound oxygen and doesn't allow any more oxygen to bind to that hemoglobin. It basically removes that hemoglobin molecule from functional capacity of the organism. So the ischemic hypoxia is a reduced blood flow. So you just don't get the fresh blood coming in to get the exchange. So heart failure, whole body hypoxia can lead to heart failure. Shock, a peripheral hypoxia, or thrombosis, so the hypoxia in a single organ. So I had mentioned that one previously. So say you get a clot that would form in the renal artery, then the whole kidney isn't getting the blood supply, and it will you can have a full failure of that kidney, or it may just be one of the smaller ones, as in stroke, as you know, and you lose a portion of the cerebral cortex. Typically, it's the one that controls the muscles of the upper extremity and sometimes the lower extremity. So histotoxic hypoxia, the failure of cells to use oxygen because cells have been poisoned. So cyanide is a prime example. It inactivates the hemoglobin. Isn't that what it does? Let's check on that. And other metabolic poisons also can cause this. So let's consider some causes of low alveolar PO2. So the inspired air has abnormally low oxygen content. Well, that's altitude. So we know that people that live at higher altitudes have compensatory mechanisms that have been in place from the day they were born, basically, because they've always experienced it. If you go to a high altitude, you have to give your body time to compensate, and these are systemic compensations. Some are metabolic, some are actual cellular, I guess, a cellular response like producing more red blood cells. The alveolar ventilation might be inadequate, so a decreased lung compliance, you just can't get it in, increased airway resistance, and an overdose of drugs. So there's a variety of these that can offset the mixing of the alveolar between fresh and stale air. Remember that discussion that we had previously. So let's take a look at this from the perspective of alveolar ventilation with a series of these cartoon illustrations. So we have the normal PO2 in the alveolus and the normal, what was it on this side and this side? It was the 100 to the, it was a 60. I'm forgetting already. That is crazy. 40 to 100. I knew it was 60. Did you remember the 40 to 100? They kept playing that 160 game somewhere along the way. Anyway, so we want to go from the 40 to the 100 across the pulmonary capillary bed, from the arterial side to the venous side, or arteriolar to the venule side if we're thinking of just a single capillary bed. If you're talking about the full pulmonary circuit, you talk about the pulmonary artery to the pulmonary vein. So what happens across that pulmonary circuit when the PO2 is normal or low with emphysema? Then you get a low PO2. You don't get the efficient exchange. You cannot blow off. Well, the CO2 is a separate thing, right? We're doing the oxygen now. You cannot refresh the air in the alveolus. The mixing is not as efficient as it should be. With the fibrotic lung disease, the PO2 may be normal or low and in the alveolar area, but you don't get the efficient exchange because you have a thickening of the membrane. So the property that has changed is the distance across which you have the diffusion. In this one, what has changed with emphysema? It's the surface area. All right, so let's see the little bulges here. We've got surface area, and there's a certain distance for diffusion. I don't know if they effectively changed that with the fibrotic one, but here we lose surface area. Well, yeah, they're showing the thicker blue line. And here you get the connective tissue thickening. So the distance from the surface of the alveolus, where you'd be standing, to the inside of the blood vessel on the AD-luminal surface of the endothelial cell. Remember, we talked about adluminal and abluminal. If you abduct something, you take it away, so abluminal is closer to the alveolus. Adluminal surface of the endothelial cell is right on the blood. So that distance from the atmospheric surface with the surfactant to the adluminal surface of the endothelial cell is the thickness we're considering here. It is increased, so you get a decreased exchange. The pulmonary edema would obviously increase that diffusion distance dramatically by creating a liquid separation, but just the same, it increases that distance of the diffusion. In asthma, you get the bronchiolar constriction, so the PO2 would be low. So here we remember the surface exchange is normal, but the distance changes. Here you get the PO2 being low inside the alveolus. Everything else is normal range capabilities, but you still don't get the effective transcapillary bed gain in oxygen. So then we can think of this gas exchange now occurring at the respiratory membrane, the exchange membrane, and apply some of those terms that I just mentioned. So it diffuses across the alveolar epithelial cells and the capillary endothelial cells to enter the plasma. When we hear the discussion in that direction, we know we're talking about oxygen from alveolus into the plasma. CO2 would be the opposite, going through the endothelial cell to the alveolar. So we see the alveolar content of oxygen. So picture yourself on this oxygen molecule. You would first encounter the surfactant, and then the alveolar portion of the cytoplasmic membrane of the type 1 alveolar cell, the alveolar epithelium. Then the basal layer of the cytoplasmic membrane, so you've got to get through all the cytoplasm of the cell too. Then the basal lamina, they're calling it a fused basement membranes, but it isn't. The basement membrane has two parts: basal lamina that comes from the cells, and reticular lamina that comes from the fibroblasts, the connective tissue. I remembered it this time. And at this point, you don't have a true basement membrane. You have two basal laminas: the basal lamina from the alveolar epithelial cell and the basal lamina from the endothelial cell. Its abluminal layer secretes a little bit of connective tissue to stick to the underlying surface. Well, here you're just getting the two cells sticking to each other. So it's really important to understand that. If it's a basement membrane, it's pathological. You've got a fibrotic condition where you have the reticular layer of the basement membrane coming in here and physically separating these and increasing the diffusion distance. So you may not appreciate the extra details always being added, but this is a critical one. It has to be understood that these are two basal laminas together. If you get connective tissue in here, the reticular lamina making a true basement membrane by strict definition, it is pathological, and your distance will be on the higher end into the values that would exceed that and compromise the rate of diffusion. So when a red blood cell goes past here, it has that momentary opportunity to pick up the oxygen. You decrease this rate of oxygen diffusion, and if the RBC is going by at the same rate, it's not going to pick up as much oxygen as it could have if you were getting more delivered at normal homeostatic rates. So remember, we've got the AB luminal cytoplasmic membrane of the endothelial cell, the abluminal, and the adluminal, to distinguish these two, and the cytoplasm in between. Then you are finally into the plasma. so dissolved oxygen in a liquid. So this is different than what we were thinking about. There was a barrier between the gas and aqueous interface when we're talking about here, and this is called the respiratory membrane, made up of these components that I just delineated. Once in the plasma, of course, then the RBC is there, and you're going to have some events taking place there that we'll consider in a while. So the gas exchange, then we think of the pathological changes. You can have a decrease in the amount of the alveolar surface area, we saw, increase in the thickness of the alveolar membrane, increase in the diffusion distance between the alveoli in the blood. So you should be able to link these to the ones that we saw in the cartoon illustrations. I'm not going to do it. I'm going to leave you to do it so that it reinforces that in your own mind. Now let's transition to the oxygen transport. Let's consider arterial blood first, the oxygen coming in, and then ultimately getting delivered to the cells. So this is occurring simultaneously. When an O2 molecule is coming in at the lung, we want to think of an O2 molecule going from the blood into the tissue. And as well, the CO2 is going in the opposite direction. But we're going to reduce it to these simplistic approaches, and we're going to follow the oxygen molecules if you were sitting on it. So if you were the oxygen molecule or riding with it, this is what you would experience. You got drawn into the alveolus, and you're at a higher pressure, so you're bouncing around and pushing, trying to get across this membrane, and you do. And you get into the plasma through what we just talked about before. This is highly illustrative now. About less than 2% is dissolved in the plasma itself. So if you were in that minority number of O2 molecules that just came in, you would stay dissolved in the plasma. Obviously another proportion is going to get into the red blood cell. And when we bind that to the hemoglobin, of course, we sustain this concentration gradient. So we will, as long as there's hemoglobin to bind the oxygen when it comes in, you sustain the concentration gradient of plasma to red blood cell cytosolic concentration of unbound or free oxygen. So that is really critical. If all the hemoglobin in a red blood cell becomes saturated with oxygen binding to it, or something else, like the toxins or the carbon monoxide, then the oxygen stops coming in. And then about 98%, we all knew it was going to be 98%, but we just had to wait till it got there. Don't want to anticipate these slides, right? And then, of course, the red blood cell is going to be circulated and transported, and it is the oxyhemoglobin. The term is what I'm going to use for this, the hemoglobin with the oxygen bound to it. And something will cause it to change its affinity, the hemoglobin, such that it doesn't want to bind the oxygen anymore, and it lets go of it. So this is a big thing that we're going to talk about, is what is the local environment here that favors a high affinity of the hemoglobin for the oxygen, and while it's being transported, and then when it gets to the capillary beds, what favors this reversal of that affinity so that it lets go of it, and then you get a reversal of the concentration gradient to pump it out of or have it diffuse out. It's not pumped out. Diffuses out into the cytoplasm and then diffuses across the endothelial cell and into the interstitial fluid and then into the epithelial cell. So always think of all the barriers. What will it encounter along the way? They make it seem here like whoosh right into the cell, but it's the adluminal endothelial membrane, abluminal, right? Interstitial fluid, then the cytoplasmic membrane of the cell, and then it's into the cytoplasm. At the same time, quite obviously, when this O2 gets into the plasma, it is dissolved in the plasma. and of course that is used in the cellular respirations. So I think I would have shown this one going to the dissolved in the plasma, and this coming in here. So the draw of oxygen into the cell as it's used for cellular respiration is the end point of this molecule coming in from the atmospheric air as oxygen, and that, if you want to think of it, is the sink that pulls that sustains the concentration gradient pulling from the oxygen dissolved in the plasma. So if this is going to leave this red blood cell, you have to have a higher concentration here than here, so it'll go into this. This will have a transient high, but there's such a sink to draw it out that it very quickly so the rate of diffusion would be very high. In other words, we are going to see a slight shift in this 2% there, and certainly this is going to change because we're going to let go of most of the oxygen that we had bound. Now for the oxygen transport, we consider that hemoglobin increases oxygen transport by the blood, as we know. So I just want to see if, okay, they're going to go through the panel separately. The oxygen transport in the blood without the hemoglobin is shown in this panel A. The alveolar PO2 equals the arterial PO2. So we reach equilibrium here, 100 millimeters of mercury on the venous side of the pulmonary circuit. Let's think of it as the pulmonary circuit here, right? So the venous side of the pulmonary circuit, we're going to be back up to the 100 millimeters of mercury for PO2. And it was 40 here, so we gained 60, right? So remember, we got our arrows going equal length in both directions, so that's equilibrium. So the O2 content of the plasma is 3 mLs of oxygen per liter of blood. The O2 content of the blood cells is roughly 0, and essentially 0. The total O2 carrying capacity is 3 mLs of O2 per liter. And then the oxygen transport at the normal PO2 in the blood with hemoglobin, then we have the same PO2 of 100 millimeters of mercury on the venous side of the pulmonary circuit, but the red blood cells with the hemoglobin are carrying 98% of their maximum load of oxygen. We see that the O2 content is going to be the same. It's still the 3 mLs, right, of dissolved. And then that, the content of the red blood cells is 197 mLs of oxygen per liter of blood. So we end up with the hemoglobin adding to that, so we have what, 90? No, not quite 90. 60, almost 7 times, almost 70 times the number of mLs of oxygen per liter of blood. My mathematical division was a little sloppy there. Okay, the oxygen transport at the reduced PO2 in the blood with hemoglobin is shown in this slide. So we have the reduced PO2 to 28 millimeters of mercury in the alveolus. Then what you end up with is equilibrium at the interface with the pulmonary circuit. So here you're actually going to lose oxygen. So in other words, what the oxygen concentration is, this is what we said before, what the oxygen concentration is in the alveolus will equilibrate with what's in the plasma. So if that drops really low, then the PO2 of the plasma will be really low. The red cells will be carrying about 50% of their maximum load. We drop down to about 100. So in other words, what we're seeing is that the oxyhemoglobin, and you know it's the saturation of hemoglobin is what we're talking about, is the predominant determinant of the oxygen carrying capacity of the blood. And that, as you know, is related to the hemoglobin molecule. It's got the iron chelated within the different subunits. There's alpha chain and beta chain, so it's a hetero tetramer. Hetero meaning you've got the two different subunits, two of each, so it's hetero, and also tetra. So it's a hetero-tetrameric molecule in its quaternary structure, and within each of the subunits, each contains this porphyrin ring that chelates the iron, and of course the iron is going to be what binds the oxygen. So the hemoglobin consists of 4 subunits, each centered around an iron. So the oxygen hemoglobin dissociation curve is shown in this slide. This is essential discussion, and then we talk about anything that might affect this basic curve. So a resting cell of PO2 is shown in millimeters of mercury, is shown on the x-axis. So we're going from 0 to 100 at the alveolus. So we've got our resting cell and alveolus here, and then the hemoglobin percent saturation is on the y-axis. So when we're at 0, 0, then there's 0 PO2 in millimeters of mercury, then you're not going to have any oxygen saturation. As you increase PO2, obviously you're going to get a portion of the curve that is quite linear, then it's going to taper and reach a plateau. So you can, once you reach 100% saturation, or near 100% saturation, that is complete saturation of all the hemoglobin that is there. When each hemoglobin molecule is saturated, it is saturated, but you've got more than one hemoglobin molecule in your body, so that's what this number is reflecting, the percent of all the hemoglobin you have in your body that could possibly be saturated, right? Not each individual molecule, but collectively. So that's why you get this dynamic property of how much hemoglobin is there in the whole body, and at low PO2 levels, increasing toward normal near the resting cell at the tissue interface, systemic, it's going to be a linear increase. But to jump from resting, this is, let me put it this way, this is how the curve looks across the capillary bed of the pulmonary circuit, or across the pulmonary circuit. Remember, it comes in at 40 and leaves at 100, right? So the oxygen binding, and that's what you want, is you want very rapidly to be able to jump from about 75% saturation of the venous side to about 100% saturation on the, it's venous blood, but it is the pulmonary artery, the artery side to the venous side of the pulmonary circuit. The oxygen binding is continued as a discussion in this slide, where we begin to look at the factors, the physical factors that alter hemoglobin's affinity for oxygen. So what is going to happen at the tissue level to convince the hemoglobin to give up its oxygen? So how does the hemoglobin saturation as a percent change with the PO2 in millimeters of mercury when you add another independent variable, something that will change the pH? So remember, carbon dioxide is very closely associated with pH. So high carbon dioxide levels will make something more acidic. So here's normal. If something causes it to become slightly basic, then the oxygen will stick to the hemoglobin. The way that we talk about this type of an effect is a shift in the response. So at a higher pH, the hemoglobin saturation curve is shifted to the left. Okay, there's no shift in the 0, 0 at the x intercept point. So that's really important to look at the x-intercept. There's no shift there, but there is a shift to the left, and there's also an increase in the slope in the rising phase. But we don't see any change in the characteristic behaviors once we get past that. So you can see that the slope, it rises much faster here than here, and this is less of a slope. So when you get closer to the alveoli, then this is going to affect the rate of 100% saturation or the level of complete saturation versus when you're thinking of being closer to the tissues where you're going to be more acidic, you're going to give up the oxygen. But if you just hold the pH, so in other words, if you do a cross-section here, you're seeing what's happening at different locations, circulation, tissue, and at the lungs where you can blow off carbon dioxide and get it closer to the 7.4. Remember, these are still pretty much within the normal range that we were talking about. So if you measure the pH rate at the cells, is it different there than it is at the the systemic circuit, the cellular interface? Is the pH slightly different there within normal range than at the pulmonary end? And as you know, if it's dependent upon carbon dioxide, yes, that would be true. As you blow off carbon dioxide across the pulmonary circuit, you're going to become a little more basic. As you build up carbon dioxide in the tissue, you're going to be a little more acidic. So we are always, on the pulmonary side and tissue side, kind of drifting on either side of the normal 7.4. So at the lung, we favor by a slightly more basic pH, and at the cell tissue level, where we want to free up the oxygen from the hemoglobin, the higher production of carbon dioxide favors the hemoglobin giving it up. But if you just hold the pH constant and then you change the PO2, this is the curve that you would get. Okay, so what I've done is I've tried to take these three curves and help you understand how a range of pH from the levels of the cell to what you'd get in a venous or arterial sample to what you'd see at the right at the venous side of the pulmonary, or somewhere crossing the pulmonary circuit, contributes to the maximization of saturating hemoglobin at the lung and desaturating at the tissue. So giving up oxygen where you should and picking it up best where you should. But this is a separate kind of a study. This is where you're holding pH constant and you change the PO2 and you see over the range of the PO2 at a lower pH, more acidic pH, the curve shifts to the right, and the linear portion of the curve it has a decreased slope compared to what is considered to be normal pH of 7.4. And the basic pH, 7.6, we see a shift of the curve to the left. In all cases, there's no change in the x-intercept, and we see that the slope of the rising phase, the rapidly rising phase, is increased. So now let's apply those parameters to other physical properties that can be changed. Temperature. So at normal body temperature, we see the normal slope for the rising phase and the point at which the slope changes to shift toward plateau. So this is the way that we look at the characteristic points of this, and under no condition do we get a change in our x-intercept. So that can become very important with hemoglobin Some biophysical properties or systems you just won't see a change there, but some others you can see a change. And so here we're not changing the x-intercept. That would be changing the gain in the system. Here we're just changing the sensitivity to saturate. So you get this normal slope and rate of change as it tapers to the full saturation. At lower body temperatures, the saturation is going to be sustained, so you sustain a higher affinity at colder temperatures. At higher temperatures, you're going to give up the oxygen. So again, the slopes of these lines are very different. Obviously, the 20 degrees, the minus 17 from normal body temperature, the slope of picking up the oxygen to become saturated is very high, and the difference there, of course, we're only increasing by 6 degrees here to a hyperthermia. And it's going to be more difficult to saturate. So you'll give it up at the tissue. So if you want to think of tissues becoming warmer because they're metabolically active, then it favors giving up oxygen, right? So this is the way to transition from this simple experiment of if we hold temperature constant as a variable at 37 and we go from 0 to 100 PO2, if we change that as an independent variable, then how does the saturation respond as a dependent variable? But then when you transition to say, well, what does this mean for the tissue? Well, metabolically active tissue is going to be a little bit warmer, maybe not 43, but a little higher than this, and then it's going to be the spot where you're going to have the lowest affinity of hemoglobin for oxygen, so it's going to give it up. When the whole body reaches a slightly higher temperature, say 38, 39 degrees maybe, then the hemoglobin at the lung, if the temperature is the same there, is not going to be saturating at normal levels as well. So you see how when tissues are just warming up, they can get more oxygen by shifting the affinity. And if it doesn't cause a systemic increase in temperature, a slight hyperthermia, we're not talking about fevers here necessarily, with exercising, just a slight hyperthermia, then even the exchange at the lung is going to be, the rate of saturation at the lung is going to be a bit different. We continue then now to look at the effect of PCO2. Remember, PCO2 is going to reflect the change in pH. So a PCO2 below normal of 20 is going to be somewhat like the alkaline condition with a shift to the left and the same increase in slope. However, what we note here is that the point at which they all reach saturation is not changed. Remember, with the shift in pH, the alkaline reached 100% at a lower PO2. So when you are just changing the PCO2, other systems are coming into play to prevent that from happening. So there's a difference in changing PCO2 and having it affect pH versus just changing pH, the true hydrogen ion concentration. So there's some type of mechanism that goes on to alter the response that you see to a change in PCO2. And in part, that's dependent just on the PCO2. So, in other words, at the lung, when the PCO2 is dropping, then, and so what's important is if we look across this spectrum of 80 to 40 to 20, we can conclude that when PCO2 drops, then the rate of saturation increases. Okay, so when PCO2 drops from 46 to 40 across the pulmonary circuit, the rate of saturation increases, so you have the greatest efficiency of saturation at the lung, and then when the PCO2 increases at the tissue from 40 to 46 again across the systemic capillary bed from 40 to 46, here we're going to 80, but still the change would be the same. Then we decrease the affinity of hemoglobin for oxygen, and we let go of our oxygen. So there's two ways that you look at these types of curves. One is where you say, what is the exact experiment that's going on? We have a variable that we hold constant at 3 different levels, and we have an independent variable that we change. We change the PO2 in millimeters of mercury from 0 to 100. When we do that, when we change the independent variable, holding the second variable at a constant across that range, what happens to the dependent variable, the percent hemoglobin saturation? And then after that, we have to interpret it to say, well, where in the tissue do we see a higher PCO2, or where in the organism do we see a higher PCO2, and where do we see a lower PCO2? And it's the pulmonary circuit where we come in high and we leave low that we are shifting to the left, favoring saturation. And it is at the systemic capillary bed where we are going from a low PCO2 to a high PCO2, and we favor giving up the oxygen. Now we think of a situation where 2,3-DPG would increase in the red blood cell, and you'll have to read the textbook to pick up on that. There are metabolic conditions that lead to this, basically levels of oxygen. When they decrease, then the 2,3-DPG increases in the red blood cell, and then this will decrease hemoglobin's affinity for the oxygen to give it up. So when local oxygen levels are decreased, like at the tissue, then this is going to increase, and it's going to favor giving up the oxygen from the hemoglobin so that it becomes dissolved and goes where it's supposed to. But if you perform an experiment where you have your same independent variable, 0 to 100, PO2 millimeters of mercury, and a covariate that you hold constant under 3 conditions, normal levels of 2,3-DPG, you have no DPG present, and you add some. So from 0 to an intermediate to a high level, and you can see the effects. So note again, we do change the slope of the fast rising phase, but we also reach the point at which we get the maximum saturation in this leftmost curve, and we cannot reach 100. It stops at 90. And here we see it converging for the where there is some 2,3-DPG. So hemoglobin evolved in an environment that selected for its properties to where it quickly and efficiently picks up oxygen at the lungs and quickly and efficiently gives up oxygen at the tissue. So the maternal and the fetal hemoglobin have different oxygen binding properties. The fetal hemoglobin is shifted to the left, but reaches the same maximum. And the maternal hemoglobin is more to the right side, actually what we considered as normal in all of these. So this means that fetal hemoglobin will take oxygen from the maternal, if you want to think of it that way, right? So whatever oxygen crosses the placenta and finds the fetal hemoglobin, is going to stick to it. And that effectively takes it out of the concentration gradient. So it creates a stronger concentration gradient to draw oxygen from the maternal blood into itself. So that interplay, remember, think of it as glucose going into a cell. When glucose goes into a cell, it is almost immediately converted to glucose 6-phosphate. And then it's no longer contributing to the intracellular glucose concentration. So you sustain a concentration gradient by converting that molecule into something else on the low side of that gradient that you want to sustain. So this fetal hemoglobin very quickly picks up any oxygen that is dissolved, and it keeps the dissolved oxygen level very low in the at the placenta in the fetal circulation, so that it will be creating a tremendous concentration gradient force to suck in the oxygen from the maternal blood and pull it off the maternal hemoglobin. Okay, let's think of oxygen binding now and the total oxygen content of arterial blood in that context, and see that it depends on the amount of oxygen dissolved in the plasma and bound to hemoglobin. So I've obviously been making this point as we've gone along. So we're going to think of total arterial oxygen content in these two terms. We'll look at the dissolved first and then this as we zoom in, but these are simultaneously ongoing, as you know. So that total in the context of just the oxygen dissolved in the plasma is influenced by the composition of the inspired air, as we saw, the alveolar ventilation that depends upon the rate and depth of breathing, the airway resistance, and the lung compliance. The oxygen dissolved in the plasma is also influenced by the oxygen diffusion between the alveoli and the blood, depends on surface area, the diffusion distance, which is related to the membrane thickness, and the amount of the interstitial fluid. We saw two extremes that disrupted, that increased either of these and had an effect. And then adequate perfusion of the alveoli. The total arteriolar O2 concentration related to the oxygen bound to the hemoglobin. There's the percent saturation of hemoglobin that's affected by PCO2, pH, temperature, and 2,3 DGP. So all of these, PCO2, temperature, and 2,3 DPG would be expected to be slightly higher at metabolically active tissue. Acidity will be higher, but pH will be lower. And so these all favor a low affinity of hemoglobin, so you're going to give up the oxygen. Then the percent saturation times the total number of binding sites, so this depends on hemoglobin content per red blood cell, times the number of red blood cells. So you can have a high number of red blood cells that have hardly any hemoglobin in them, and your PCO2 that would be measured would be low, right? So carbon dioxide transport is next. So we've completed the oxygen, now we do the carbon dioxide. So dissolved about 7%, converted to bicarbonate ion about 70%, bound to hemoglobin about 23%. So the hemoglobin also binds hydrogen, and the hemoglobin and carbon dioxide, when they're combined, is called carbaminohemoglobin. So we had oxyhemoglobin, now we have carbaminohemoglobin, as it's binding to an amino acid. So we're going to follow the carbon dioxide molecule now as we did the oxygen. So we're going in the reverse direction, remember, as I said, from the site of origin, from cellular respiration in the peripheral tissues, ultimately to get it blown off at the lung. Sorry. So about 7% is dissolved. And of course, we're going to see the 93% is going to get in to the the red blood cell somehow. CO2 bound as carbaminohemoglobin is 23%. Then the remainder of the 93, I guess would be the 70, is going to be acted on by an enzyme. Carbon dioxide plus water, under normal conditions, at low levels, at low rates, will be converted to carbonic acid. And carbonic anhydrase is an enzyme that freely and reversibly will catalyze this reaction. And then very quickly the carbonic acid will dissociate into bicarbonate ion and the hydrogen ion that will bind to the hemoglobin. So here is this correlation between carbon dioxide and hydrogen ion concentration. And we say, well, this is, seems confusing because you've got bicarbonate there to counterbalance it. In this case, we are contributing more hydrogen ion to the system, but it is binding to the hemoglobin. So this is in part associated with how the pH affects hemoglobin, the oxyhemoglobin saturation. So don't let this throw you off right now. When we talk about pH balance, we'll integrate more into this. In your mind, when you think of carbon dioxide being dissolved, think of higher hydrogen ion concentration and a lower pH, an acidic situation. So as PCO2 goes up, acidity increases, hydrogen ion concentration increases, pH goes down. And you get this, if we will, acidified hemoglobin. It's actually called protonated. We've added a proton to it. Remember, hydrogen is just a proton. Then the bicarbonate is transported into the plasma, and that's where 70% of the carbon dioxide is. You see the CO3, well, that's where that CO2 is buried in there with our balanced formula equation. The water brings in the other things that we need. And then this is an antiporter, chloride in, bicarbonate out. So this, on the red blood cell surface, we have a chloride bicarbonate antiporter protein that is concentration dependent. So the more bicarbonate you generate, in other words, the more carbon dioxide that's present, then the more carbon dioxide is transported out of the red blood cell, bicarbonate, I hope I said, and chloride in. So hopefully you're seeing that in association with this, if more of this becomes available, you're bringing in the chloride to neutralize it. Okay? Or, excuse me, to offset the charge. You balance the charge, but you still have hydrochloric acid. I'm sure you caught that. Like, wait, HCl is hydrochloric acid, isn't it? But you're balancing the charge. Anyway, so the dissolved CO2 now, once we get to the lungs, so we have the transport. So the CO2 is transported, either bound to hemoglobin that just gave up its, remember, in the presence of carbon dioxide, and with increased hydrogen ion concentration, lower pH or acidity, higher acidity, the hemoglobin has a lower affinity for oxygen, so it just gave it up for the cells that need it. And now it's capable of taking on the carbon dioxide and the hydrogen that's generated to pick up the carbon dioxide load that is carried predominantly in these forms. And of course, you just put some into the plasma as bicarbonate. So that's how it's transported. So in other words, if you were asked what are the forms of carbon dioxide for transport, it would be the carboxyamino hemoglobin, or bound to hemoglobin, and as bicarbonate in the plasma, but it results in protonated hemoglobin as well. And don't forget our very important friend, the carbonic anhydrase, that's going to come back into play here. So now at the lungs, remember we said that the pressure gradient is dissolved carbon dioxide in the plasma versus the gaseous carbon dioxide in the alveolus. That's the pressure gradient that is generated. And so as soon as we get there and some of this is passing out, then it's going to reverse the situation so that you no longer are favoring the formation of the carboxamino hemoglobin, and that's going to dissociate, and then the carbon dioxide is going, remember this is freely soluble, passes freely through the membranes, so we don't need any enzyme reaction there. But where we do need the enzyme reaction, and they should show it first, is that as the carbon dioxide concentration inside the red blood cell is dropping because it's passing out here and then escaping there, as you're blowing off CO2, you're pulling it out of the red blood cell. When you pull it out of the red blood cell, you lower the right side of this equation that is freely reversible. If you take this reaction and superimpose it with this one, you've got arrows going in both directions here. So if you increase the CO2 here, you drive it towards the carbonic acid. If you decrease the carbon dioxide, you favor the opposite reaction of taking the carbonic acid and making H2O and CO2, and you continue to blow off the CO2. As you decrease the carbonic acid, then you're going to pull the hydrogen off the hemoglobin, favor the reversal of that reaction, and consume bicarbonate to reverse this free reaction. It's very rapid, so it's as soon as you start pulling off H2CO3, the carbonic acid, to make water and carbon dioxide, because you're blowing off CO2, you are automatically and rapidly deprotonating the hemoglobin, making it available at a higher affinity for oxygen to pick up the O2 coming in, right? And as well, you're freeing this up to pull it in. And you're going to reverse the antiporter, and you're going to pump chloride out as you're pulling bicarbonate in. How are you going to do that? As you are placing the draw, reversing this carbonic anhydrase reaction by blowing off CO2, you are going to be instantaneously, moment to moment, decreasing bicarbonate concentration, which favors influx of the bicarbonate, and you reverse this antiporter, and chloride is pumped out. So the summary of the O2 and the CO2 exchange is shown in this slide at the alveolus. I'll let you look at the air one. Let's just look at what ends up in the alveolus. PO2 100, which matches the venous side of the pulmonary circuit. The PCO2 40, which also matches the venous side of the pulmonary circuit. And when we are considering the CO2 transport, 70% is in bicarbonate, 23% is in the carbon dioxide bound to the hemoglobin, and 7% is dissolved. The transport away from the lungs for the oxygen, the O2 transport is as the oxyhemoglobin, 98%. The dissolved is less than 2%. And this gives an approximate PO2. Then at the tissues, the PO2 is approximately 40 millimeters of mercury. PCO2 is about 46. So they represent the systemic venous circulation, which is, of course, the pulmonary arterial value as well. So in other words, a venous blood draw will be representative of what the tissue should be experiencing. And arterial will represent the pulmonary function, how effectively the pulmonary circulation is generating the PO2, PCO2 that should be delivered to the tissue to sustain homeostatic levels. So there is an animation for you to view